Hi everyone. Today we're looking at the properties of amines. So we're focusing on their shape, their boiling points, and their solubility in this wee video. So you should be on page 7. Let's get started. The shape of the amines is very similar. In fact, it's the same as ammonia. So we describe it as pyramidal and it has a bond angle of 107 degrees. Now, if you remember when we studied shape in year 13, this shape comes as a result of repulsion. So we know that there's a lone pair of electrons on the nitrogen. Lone pair to bonding pair repulsion is greater than bond pair to bond pair repulsion. So there's a great repulsion coming down from that lone pair on the nitrogen, pushing those bonding pairs closer together, causing this bond angle of 107 degrees. And no matter, whether we replace a hydrogen with an R group or not, it's still a bonding pair. So we will still have this angle because we will always have 3 bonding pairs and 1 lone pair when it comes to the amines. Now, when we look at the amines and we think about their boiling points, we have to start by thinking about the polarity. Because remember, boiling points are determined by the intermolecular forces. So if you look, now I know I've got ammonia here and it's not the amines, but it works very similarly. Imagine the lone pair is on the nitrogen. That means your nitrogen is slightly negative compared to your hydrogens and your R groups, whatever you would have. Okay, so there is a polarity there. So the first thing we can say is that the amines are polar molecules because the nitrogen will always be more negative than your side groups here. The next thing we can say then is that they've got quite high boiling points then as a result of that, and that's because of our rule with hydrogen bonds. Remember, nitrogen, oxygen, and fluorine, if they're bonded to hydrogen, can form nitrogen bonds. So we have nitrogen here forming our hydrogen bonds. We also then have to realize that shorter chain amines are gases at room temperature and pressure. That's what RTP stands for. So the shorter chain amines have got quite low boiling points to be gases, and then your longer chain amines are colorless, volatile liquids at room temperature and pressure. Those are the main points you need to know about boiling points. However, questions come up more so related to comparing amines to other molecules, and we're going to look at that now. Here's your typical question. Explain this difference in boiling points. So we've been asked about methylamine, and we've been told the boiling point is 278 Kelvin, and then we have methanol with a boiling point of 338 Kelvin. So we can see the boiling point of methanol is higher than methylamine. So let's look at our main structures. Now this is a general picture for structures, but what you can see here is you can see there's a hydrogen bond between this amino group of the amine, and then we have our polar bond between nitrogen and hydrogen. Here we have on the right hand side, we're looking at methanol. So we've got a polar bond between oxygen and hydrogen, and a hydrogen bond then between oxygen and hydrogen of different molecules. What you want to do here, remember, when you're looking at difference in boiling points, is look at the electronegativity of this oxygen and this nitrogen. And if you have your periodic table there, or if you're starting to remember it because you're so used to looking at it, you will know that oxygen is right beside fluorine, which is described, remember, as the big daddy of the electronegativity. So it's the most electronegative. Then oxygen's beside it, and then nitrogen's beside that. So oxygen is more electronegative than nitrogen, which means the bond will be more polar and the hydrogen bond will be stronger. And it's this hydrogen bond that dictates the boiling point. So the one with the stronger hydrogen bond will have the higher boiling point. So our little explanation we could write here on page 7 is oxygen is more electronegative than nitrogen. So the hydrogen bonds in methanol are stronger than in methylamine. Therefore, more energy is required to break the hydrogen bonds in methanol than in methylamine. Take a minute and write that in for your explanation. Next thing to look at then with boiling points is to do with contact, and we talk about this at AS all the time. So this is really just taking our knowledge that we learned last year and bringing it back in this year. It applies to more than just one aspect of chemistry. So the more points of contact we have, the more intermolecular forces we will have, and therefore the higher boiling point. You know that. So let's look at these examples. We've got butane 1-amine. Okay, so here we've got a main chain of butane of 4 carbons, and the amine group is on the first carbon. So I have drawn that there, and we've got a boiling point of 78 degrees Celsius. The next structure we're looking at is butane 2-amine. So we've still got our butane chain of 4 carbons, but this time your amino group is on the second carbon. So it's not part of the main chain. In fact, this time it would be classed as a branch. And you can see here, butane 2-amine has got a boiling point of 63 degrees Celsius. Look at the points of contact we could have. It's so easy to see that butane 1-amine on the left quite easily will fit nice and neatly with other molecules, whereas butane 2-amine won't fit as many in. So we can see with butane 1-amine, there's far more points of contact, therefore more intermolecular forces and a higher boiling point, whereas butane 2-amine has got fewer points of contact, fewer intermolecular forces, and a lower boiling point. So that's really what we're looking at here. Make sure you draw in 1 molecule of butane 1-amine and 1 molecule of butane 2-amine in your notes. So pause and draw them in. We've got 2 more examples, and you can see I've worded it slightly different at the top here. So, we could say more contact, higher boiling point, or we can say more branching, lower boiling point. So the first example we have is diethylamine, okay, and it's got a boiling point of 56 degrees Celsius. I want you to pause this now, and I want you to write that in. It's a diethylamine. So 2 ethyl groups and your amino group. Pause now and write that in. The second one I want you to do then is dimethylethylamine. Pause again and draw that one in. Okay, let's check your answers then. Here is diethylamine. Now you could have written it in its basic structural formula, but I've gone for skeletal because it becomes more common in A2 and it's a wee bit quicker to draw. So we've got diethylamine and then we've got dimethylethylamine. So which one has the more branching here? Yeah, the one on the right has got more branching. So it's going to have the lower boiling point, as we can see there. Okay, whereas the one on the left is more of a straight chain molecule. It's only got like 2 branches coming from it. The one on the right has got 3. So that's everything we're looking at to do with boiling point. Let's move on. Turn to page 8 with me. Amines are smelly. They're really smelly, and they're not good smelly. Normally in chemistry, you get to smell things like esters, smelling like pear drops, ethanol's vinegary. We can cope with that. It reminds us of chips. Amines smell like fish. So you know that smell at the fish counter. It's not what you want. I mean, you wouldn't spray it around your home. You don't want to smell a fish. That's the first thing you need to know there in terms of their smell. But I want you to know why. So the reason is when proteins decompose, and we will look at proteins. I'm not going to focus on it now because we're going to look at it in one of our topics to come. But when they decompose and break down, diamines and triamines are produced. And those diamines and the triamines are what cause the fishy smell, or like a rotten flesh smell. So it's the amines that are responsible for the fishy smell in rotting flesh. So you can blame them. The positive is they're easy to spot out. So if you were ever asked to identify an amine, you could do it very easily. Now, the last property we're going to look at is solubility. So we're looking at the solubility of the amines. And the first thing is primary amines up to 4 carbons are very soluble in water. So up to butylamine or butan-1-amine, they're very soluble in water. But we need to know why, and we need to write that down. And your reason here is that the lone pair of electrons on the nitrogen atom allows them to form hydrogen bonds with water molecules. So it's the lone pair on the nitrogen atom that allows them to be soluble. And with the short chain, then they have the freedom to do that without being blocked or being interfered with. So stop this now, pause it now, and write in the reason why on page 8. On the other hand, larger chain amines like phenylamine that we've got here on the screen are not very soluble in water. So the complete opposite. As our carbon chain lengthens or as it gets bigger, we find that solubility decreases. And why? Well, the reason here is that larger hydrophobic carbon chains interfere with the hydrogen bonds. The hydrocarbon chains are unable to form hydrogen bonds. And in fact, they kind of just hate the idea of being soluble. And so we describe them as being hydrophobic. And they largely outweigh the hydrophilic end. And hydrophilic is like water liking. So they largely outweigh that lone pair's ability to be soluble. So it's like a weighing up game. If you've got a short chain of carbons, then the hydrophilic end can take preference. If you've got a larger chain, the hydrophobic end takes preference and it interferes and doesn't allow the hydrogen bonds really to form because it gets in the way. And it's all this like physical distance space idea. But two simple ideas. Short chains dissolve because they can form hydrogen bonds easily. Long chains don't because that carbon chain interferes with the hydrogen bonds. So pause that now and write your reason and why. And what you can do then, this is kind of the end of this wee video. So you can read that wee bit below it. Phenylamine is what's in the lava lamp. That's why I have a lava lamp at the side of my room. I always go on about it. So you can read a wee bit there. There's a couple of lines about how phenylamine acts in a lava lamp. I think it's amazing. I love the amines. I mean, I don't love to smell them because who likes a fishy smell? But I just love everything else about them. So you can pause this, make sure your notes are up to date so far before we move on. And once you're done, read that wee bit that's there on page 8. And then we're going to move on to the preparation of amines. Chat soon.